We will now be starting this new session in 2 minutes, and I invite Professor Sudhir Ghorpade from Indian Institute of Technology, Bombay, to chair this session.
Okay.
So I request Professor Sudhir Ghorpade to come here and chair the session.
Thank you, Professor Katre. Thank you, everyone. We still have 1 minute, but I think we can begin the session. So it's welcome to this second session. Good afternoon to those of you who are here in India. Good morning, Professor Jiang, and those who are in the US. It is my pleasure to introduce our first speaker of this session, Professor Yunping Jiang, from Queen's College and the Graduate Center of City University of New York. And he will speak to us on a function model for the Teichmüller space of closed hyperbolic Riemann surface. Professor Jiang, please.
Okay, thank you very much for introduction. And also it's nice to attend this meeting, celebrate Ravi's 80th birthday. I know Ravi for many years, more than 30 years. So also I have 2 Indian students. So I think it's nice to give a talk in Indian conference. Okay, my title is a function model for Teichmüller space of a closed Riemann surface, right? Let me start it. Okay, so why cannot go? Cannot move. Right. So okay. So first, let's see what is a closed hyperbolic Riemann surface, right? So you think the unit disk as a hyperbolic disk, right, with the hyperbolic metric that's the dz of 1 minus z x value z square, then square d square, right? So closed hyperbolic Riemann surface can be viewed as a quotient space of a unit disk, hyperbolic disk modeled by a so-called function group, right? Co-compact function group. A function group is made by asymmetries on the hyperbolic disk, right? So then if you consider as a Euclidean disk, then you have a boundary is a unit circle. So then for Riemann surface, we have something called a genus, right? That is topological invariance. That's a topological invariance. That means 2 surface closed hyperbolic surface are topological equivalent if and only if they have the same genus, right? So here's 2 graph about one is genus 2, one is genus 3, right? That's hyperbolic Riemann surface looks like. So then as a quotient space, the hyperbolic surface can be viewed as hyperbolic polygons on the unit disk, right? So if you cut the Riemann surface along some curves, most time you cut along the geodesics, right? Then you can form polygons, right? So actually, there are many ways to cut a Riemann surface. So I present here is one is cut into the 8G minus 4 gun. Another way you can cut into 4G guns, right? So then you cut the all these hyperbolic polygons, right? Then you have a fundamental domain. Here is a fundamental domain F, right? FG here. So now I'm going to use the 8G minus 4 guns, right? I'm going to use the 8G minus 40 guns. In my previous paper, I used these 4G guns. So either way is okay. But let's see. So first, you cut this guns, then you have a pairing on the boundary curve, right? So here's next slide, see how these sides of the 8G minus 4 fundamental polygons can be labeled, right? So we label this all the sides of the, so here's the sides, right? So this is the sides here, this size here, this size here. So we label all of these sides as from 0 to the 8G minus 5. We label it counterclockwise, right? Counterclockwise. So each side was paired with another side. Actually, I wrote down the formula how to pair two different sides together, right? So you pair I with 4G minus 2 minus I, but it has the modular 8G minus 4, right? If I is even, or minus I if I is odd. But you definitely need a modular 8G minus 4, right? So then every side actually can be extended to the, if you look at this picture, every side actually can be extended to the boundary of a circle. Then you have two endpoints, right? You have two endpoints. So those endpoints we label as P0, Q0, P1, Q1, P8G minus 5, Q8G minus 5. So this point actually arranged counterclockwise on the unit circle, right? As 16G minus 8 points, right? So here's a picture we show how to arrange this point, right? You have a P0 here, then you have a P1 here, but then between here you have a Q1, then you have Q0, you have Q1. So then so on, right? You arrange the counterclockwise. So then this point will be cut as a unit circle into the 16G minus 8 intervals, right? Intervals, which interval we call the eta. We use eta to means that a partition, right? You have a circle, then you partition it into the many intervals. So then I2i denoted as pi qi, I2i plus 1 denoted as qi pi plus 1. You modulo 8G minus 5, right? So now you have this 16 minus 8G intervals. So here's all the intervals, right? So let's see. So here's all the intervals. So that is one intervals. That's another intervals. That's intervals. That's intervals. That's among these intervals, you have a bigger interval like this, right? You can think of this P1 to Q1. P1 to Q1 is actually we call the J0 and so on, right? So then we use the Ji is actually a little bigger interval, is Pi. Let's see, Pi, okay, here's J is actually from P0 to P1, P1 to P2, P2, P3, P4, right? So then on each interval, you see you have a pairing map, which is in the group, right? So you use the pairing map as gamma I, which is in the group. That's gamma I paired I and Pi, right? So now, okay, so now you take the interval Ji, which is pi plus 1 for I from 0 to the 8G minus 5. So then on each interval, you define a map as gamma I, right? On this interval, you define this map gamma I, because gamma I is actually defined how the unit disk, right? Even how the complex plane. So you define this gamma I on interval Ji. So then you got a so-called one-dimensional dynamic system. So it actually is so-called a Markov and expanding one-dimensional dynamical system. So the Markov means what? Markov means every interior of interval. I found that every interior of interval is 1 to 1. And f of j, image of f I, is the union of some interval in eta, right? It's a union of some interval in eta. So that is a so-called Markov property. In actually, this one is from a probability theory, also in dynamic system, right? So now, what does expanding means? Basically, expanding means the derivative is bigger than 1, but since our definition, some derivative may be 1, absolute value may be 1, but you iterate it several times, derivative will be bigger than 1. So then, formal definition about expanding is actually, so there are two constants, c bigger than 0, lambda bigger than 1, such that the derivative of f to the iterator up to the n bigger than c times lambda n for all the x, such that f prime exists on the orbit. Because remember, our map is defined piecewise differentiable, right? So on endpoint, they may not be differentiable. So then you have to make sure derivative exists for every orbit, right? So that is, so here's a graph which I show what is the Markov map looks like, right? For example, this interval, your image is a 4, 2 interval. This interval, your image is all the 1, 2, 3, 4 interval. So this interval, you have all the 3 intervals. So here's the cover 3 interval. So also sometimes if they cover Hall, then you can see these 2 points will be not 1 to 1. Only on the inside, interior is 1 to 1, right? So that is a way you define the Markov map. So then what is good about this Markov map give it to you? So if you have a Markov property, then you can also pull back the partition to get a sequence of nested partition, which is called eta n. So that means
Yunping, I'm sorry, can I ask a question? Hi, it's Dragomir.
Go ahead, yeah.
So do you mind just going back and showing which is interval I sub I and J sub I? There are 2 intervals.
Okay,
on the picture.
In this picture, okay, let's see, the iris order. Okay, here is I0, I1, I2, I3. That's I0, I1, I2, I3, so on, right? So J is actually here. So it's from P to P. So for example, this is J3. That's J3. Okay.
Okay, thank you.
Yeah. So, okay, so you have this Markov expanding property now. So then the point is Markov property will give you the pullback. You got a sequence of nested sequence of partition, right? So that is eta. So that's eta 1. So oh no, that is eta 1. You can see eta 1 is actually every interval is cut again according to this rule. Later I will mention this called a matrix rule, then there's Markov chain property. So okay, so the point is expanding property show us this interval, and then interval where we go to length where we go to 0 when this size n go to infinity. So that means every next interval, if they contains 1 point, then you eventually shrink to a point. Okay, so that is a partition. Now I'm going to come to the so-called symbolic dynamical system, right? So the reason is if you give a Markov partition plus expanding, all dynamic system, it looks like a one-dimensional or different one, but actually they have a topologically, they are exactly the same. They are actually called a symbol, always conjugated to this symbolic dynamic system. So what a symbolic dynamic system is? So you take the B is actually is a set of integer from 0 to the 16g minus 9. Then you can get a matrix, actually 16g minus a times 16g minus a matrix called A, capital A equals Aij. So what is the entry is? That equals 1 if Fi contains Fi contains Fij. So that means that's I. If that is contains this Ij, right? Its image contains here, then we call the 1. Otherwise, 0, because according to Markov partition, a Markov property, this either contains Howard interval or none, right? So then you can define the 0, 1 matrix. So after you define the 0, 1 matrix, right, you can define so-called symbolic space we call the sigma A. So that means it's all the string of the integer within B, but such that consecutive integer must be have that property. That means that you can really apply the F to map I to J, right? I to J. So then on this symbolic space, you have something called the shift map. That means you knock off first digit, right? So you got here. So that's shift. So that's this shift really means like F map X to the F of X. So then if you trunk this sequence to the Wn, right? You take the n length n strings, then you can use that one to label every intervals in eta n. So that means every interval in eta n, you have a unique labeling Wn, which I denote the IWN, right? Before I just cut, but now I give an address for every interval. So now the key point here is if you put a digit on the right-hand side of this digit Wn, then you get a subinterval. If you put this digit on the left-hand side of this Wn, you get a pre-image, right? So here's Wn here. So then if you put a IWN I here, that get a subinterval. If you put a I here, so you get a pre-image, one of a pre-image. That means I really should do this way. Really should go this way because F is not 1-to-1, it's a many-to-one map, right? So now then key point is here is actually F acting on XW. So XW is you can give every point address like use the symbolic space, right? XIW is actually intersection of IWN. So now point is F acting on this IWN just like a shift on the W, right? So that is the so-called symbolic dynamic system for all the Markov map which has same matrix A. So now let's talk about something called the dual symbolic space. So what is dual symbolic? Dual symbolic space is like this. So first, when we do the symbolic space, we read a digit from left to right. But now we read a digit from left to right to left, right? But then we have exactly same symbolic space, but the shift now is just knock off most right one. So then you can see, because as we know, if we knock off most the right one, then we get a upper interval, right? So that means this one. So then you get actually here. So that is Wn star. Then you knock off this one. I got okay. Here's Iwn star. So then you left shift. You get sub interval. So here is but actually we have to see that Wn star equals Wn from digital point of view, but only the different way to read it. In topology means there are different topology, right? So Wn means you read a digit from left to right. Wn star, you read a digit from right to left, right? So now we consider the ratio of these things. That is a sub-interval of that. We can take a ratio of two intervals. So this ratio is we call the pre-scaling. So then you can see if you do the shift, right, you actually you keep adding the digit on the right, you actually get a pre-image. So that is a picture you see here, right? So now the we talk about what is limiting map. So then you see that theorem is for every W star in this dual symbolic space, then limit along this dual topology exists and define a Herder continuous function, right? Herder continuous function. So then we actually define the so-called Herder continuous function. The wise reason is Herder because this one is actually metric space, right? You can assign a metric. And Herder means that S W star minus W star prime is less than ups value less than some D, the metric you have D, right? D W star prime to some power alpha. You have some C here. So as long as yeah, that is meaning about Herder, right? So now for hyperbolic Riemann surface, now we can define Herder continuous function associated with it, right? This function we call the scaling function of this Riemann surface. Okay. So now what is the relation between this scaling function with the Teichmüller space? So okay, first, if you take a fixed hyperbolic Riemann surface, right? Usually we take the standard one, whose fundamental polygon is a symmetry, right? Which called a full domain, very regular one. And then Teichmüller space is really the marked Riemann surface up to the homotopy to identity for conformal equivalence, right? So here's I wrote down the one definition about this Teichmüller space, but there are some other way to write this definition. So now the key point now is so people is familiar with Teichmüller space, then you don't need to read it, you know it. But if you don't, just read some standard reference about Teichmüller space. So now the key point I want to see is here. So scaling function of two closed hyperbolic Riemann surface of same genus, right, are same if and only if they are Teichmüller equivalent. That means you have R1 is Teichmüller equivalent to R2, right? If and only if the scaling function actually is same, right? Scaling function same. So then what is you see? Then you can actually the scaling function is really defined on the Teichmüller space, not only for hyperbolic Riemann surface. It's actually its function for every point in the Teichmüller space. Now you take all the scaling function, right? You get the SG. This SG we take as space of all the scaling functions for all the hyperbolic Riemann surface of the same genus G bigger than or equal than 2. Then you have a actually injective map, or surjective map, actually bijective map, right? injective and surjective bijective map from Teichmüller space to this function space. So then we will call this function space as a function model for the Teichmüller space. Okay, so now you define a different model for Teichmüller space. So now what is useful? Let's see. Let's see that. First, you have a Teichmüller metric, right? So on the Teichmüller space, we have a standard so-called Teichmüller metric. So for the Teichmüller metric, which actually is a Kobayashi metric, if you think of the Teichmüller space as a complex Banach manifold. But then this embedding so bijective map will actually introduce a Teichmüller metric on the function space. But another that means first you have a function space here, you have a Teichmüller space here, you have function space here. So here you have Teichmüller metric, then you can define the same Teichmüller metric on function space, right? So now, but another important thing is for the function space, right? Consider this all the continuous function on the sigma A. As we know, sigma A is a compact metric space, right? So then every function has a maximum norm, right? You take maximum value of the function. So that's called the maximum norm. So maximum norm. So then you can introduce so-called maximum metric on the Teichmüller space now. So that is defined as maximum norm of this difference of these scaling functions. So now we introduce a new metric called the maximal metric. Then you have a question is that a maximum metric is meaningful, right? So that means you do not want to introduce a metric which has very different from a Teichmüller metric, right? So what does that mean? That means do they have the same topology on the Teichmüller space? So here's a theorem I proved is like this. So the identity map from this Teichmüller space with the Teichmüller metric to the Teichmüller space with its maximum metric is uniformly continuous. But then inverse of this one, so that is inverse also identity map from a Teichmüller metric with the maximum metric to the Teichmüller space with Teichmüller metric, but that's only continuous. So then one side is uniform continuous, one side is continuous, only continuous. However, they introduced the same topology, right? Because identity map is continuous. So they introduced same. So that means maximal metric is.
Yunping, I have a question.
Yeah.
Sorry. Can I ask a question?
Yeah.
So can you go back to the slide? So do you know that the map is continuous and not uniformly continuous, or you just know it's continuous but not clear that the other way around?
Yeah, it's clearly not a uniform continuous. Depends on when you approach the boundary of the Teichmüller space, this maximum norm actually could be very small, but Teichmüller metric could be very big.
Okay, thank you.
Yeah. Okay, so now we the reason we introduce this function model is because we can bring a lot of concept in dynamic system into the study of this Riemann surface, right? So first thing in the dynamic system, there's a very important concept called topological entropy. So actually, there's a very good paper if someone wants to read about how to use this thermodynamics to study this. Let me just write this reference called R. Adler and L. Flato. So they have a paper really show how to use dynamic system to study this So that's actually is 1991, the bulletin of AMS, right? So so in this paper you can use that one. Actually, another recent paper is actually by Brian Katok. And Yugasakovich, right? So that is pre-printed now. So they actually have some good study, but now I try to see what I studied, right? So here is, so first for this matrix A, which is aperiodic, or another word is called irreducible. So that means you have some integer n such that a to the power n is a positive matrix. That means every entry will be positive. Translated to dynamic system is like this. Every interval you iterate n times will be cover whole the unit circle, right? Cover whole the unit circle. Then this positive matrix, then the Perron-Fubini theorem tells us that A has a unique maximal positive simple eigenvalue, which called lambda maximal. So then log of this lambda x is so-called topological entropy of this shift map. So then use this cutting. Also, if you look at how this matrix looks like, right? Because every interval you map to some other intervals, so you can actually concretely write down this matrix A. You can calculate maxima eigenvalues like this. Also, then topological entropy is like this. I think in the current paper, this they actually calculate that, but actually from Adler, Flatter's paper or picture, you can really calculate the matrix A. So now, what is topological entropy good about for study of hyperbolic Riemann surface? So topological entropy really tell you how this complicated of closed geodesic on the Riemann surface, right? Then you can see this kind of closed geodesic will not change with shape of the Riemann surface, right? That's actually topological invariant. So topological entropy is the topological invariant, right? So measure how complicated of this simply closed geodesic wrap on the Riemann surface. So then you can see that is a constant on the how the Teichmüller space, right? So another thing is you can introduce so-called thermodynamical formalism into this study, right? So suppose you have a S. Remember, our S is so-called Herder continuous function. Then the classical Gibbs theory said that you have a unique probability measure, mu on the sigma A, such that this mu on every cylinder, right? Cylinder is actually is open side in the sigma A. Every cylinder, which is compatible with orbit, right? Observation of orbit, right? You take a log of S, we call the observation. Then if you think of the orbit, right? So here you have W is here, so you have that's a block, right? Cylinder. Then W will be mapped to by sigma to a lot of things, right? You have a sigma star. That's we take a sigma star here. So I have an image, right? Sigma. Right. So then you have on each point you have a so-called observation called the log S, right? So if you sum of this observation, that's actually similar like a measure on the cylinder, on this cylinder, but with the correction. But this correction is actually equal 0 always in this case. So basically, this one equals 0. So this number called the pressure called the pressure in thermodynamical formalism, right? So, okay. So now you have a measure, you have a pressure for associated with the Riemann surface knot. So now you can define something called a pressure metric on the space of scaling functions. So what is pressure metric? Pressure metric is you take a smooth curve, right? So here's SG. You take a smooth curve like ST here, right? You pass some point S0 here. Then you take a log. Then you take a derivative. This is a derivative. That's actually this one. This one really means a derivative log ST over dt, take t equals 0, right? So that is like a momentous, right? Like momentous. Then you integral, since we know this p log st is always equal 0, right? That right, then derivative definitely also equals 0. So, but the derivative equals mean actually. So actually is a mean. So that since the way mean has 0, so we can calculate the pressure metric on the Teichmüller space tangent of this space as this formula, right? So you take this log here is so here's a variation. So that's a variation. You just calculate like this, called a variation. So now what is good about this pressure metric? Pressure metric have a very well connection with so-called Weil-Petersson metric on the Riemann surface, on the Teichmüller space. So, okay, yeah, classically you define the Weil-Petersson metric, use that one, right? Use the so-called harmonic Beltramian differentials, right? So then that is a classical way to calculate the Weil-Petersson metric. But then you actually use this pressure metric. You can calculate this Weil-Petersson metric. So actually, this pressure metric connection of pressure metric and Weil-Petersson metric has been studied by many people, like Macmillan have a paper on this, but use another way to define that. This where you can check. A lot of people study that. So that is a connection between Weil-Petersson metric and this scaling function, right? So that's one thing. So now another thing is so-called metric entropy. So topological entropy is measure the global complexity. That means how does a closed geodesic wrap on this Riemann surface, right? But then they will not tell you how far and how close, right? But this metric entropy tell you this how far, how close this closed geodesic, right? So now the metric entropy is actually can be okay. So metric entropy of metric entropy also called a measure theoretical entropy, or called a Kolmogorov-Sinai entropy. But we calculate the metric entropy for this Gibbs measure, right? We have a particular way to calculate the metric entropy only for the Gibbs measure. So so now this metric entropy calculated for Gibbs measure actually have a very well defined formula. That means you just integral on the sigma A of log S W star D mu, right? So then actually then you can see this metric entropy define a function. Actually, this continuous function or even smooth function from the SG to the 0 H0, right? So actually you can really calculate this metric entropy. Actually use the paper. I means I talk about this Adler and Flatter's paper. Also, other people recently also calculate this. So then you can see this metric entropy is really well-defined function from this space SG, function space. So as I just said, this meaning about this metric entropy is really the measure how so-called level of complexity. In other words, means measure in Riemann surface measure how close and not only complicated of how close geodesic rub on the Riemann surface, also measure how far and how close they are. But I mean in the measure point of view, right? So now you can see this which metric entropy actually is touch the maximal at the base point of Teichmüller space, but then go down to the 0 here. Okay, so that is metric entropy. Also, that's why you introduce function space. You can study the metric entropy for the Teichmüller space. So now, I think I still have a few minutes, but I'm done already actually. So now actually, now you come back to the Teichmüller space, right? We know Teichmüller space is homeomorphic to the R6G minus 6, right? It's actually basically it's finite dimensional manifold, right? So also it's a pseudo convex domain. TG admit a complex structure of a 3G minus 3, right? And the TG can be embedded into this C3G minus 3 as a contractible set, right? So now C and D really talk about this function space also have a complex manifold structures and also contractible. But A said, okay, so if you look at a function space of continuous function on the sigma A, that's the infinite dimension, right? You have a lot. But then this function space of Teichmüller space are basically only finite dimension. So that means not every continuous function will be qualified for this scaling function of Riemann surface. Then we have a question, actually it's a problem. So how do you calculate a character? How can you calculate character a function in the scaling function, right? As a scaling function of a hyperbolic Riemann surface. So that is still a problem, right? In other words, how is that an SG is a pseudo-convex or not? That's something we don't know yet, but we try to study it. Okay, I think I'm done. Okay, thanks. Okay, thanks.
Okay, thank you very much, Professor Jiang.
Thank you.
Are there any questions or comments? People who are online can just unmute and ask their questions.
I have a question. So
yes,
can you just remind us again, what is the scaling function? Just quick definition. I think I missed.
Okay, right. Yeah, here's a definition, right? So you have first you have a sequence of partition of intervals, right? Then you take every interval, you have a labeling called IWN star, right? So you have an interval here, okay, here's a IWN star, right? So now you use a shift, you actually go up to is a parent interval, right? Then you consider ratio of these two, okay? That's the ratio of these two. But then you take the backward image as a limit, not like a regular symbolic space limit. Like you take a backward image as a limit. But that limit exists. Actually, regular symbolic space limit doesn't exist. So backward image, that means you have this one, you keep a backward image, backward image, right? Backward image could be like this. Then eventually we'll be landing on some point on the sigma A star. So that limit exists.
Yeah. Thank you.
Yeah. So that is the definition. Yeah.
So what kind of applications do you have in mind with this?
Application?
Yeah.
So for example, use that one, you can easily calculate the topological entropy. Also, topological entropy tell you how the growth of the closed geodesic, right? Basically. Also, you can calculate the so-called metric entropy, right? Tell you how this simple closed geodesic wrap on the circle, how close, how far, you know, these kind of things.
Can you see the complex structure on this space from first principles?
So you have a complex structure on the ISG, right?
So we know that. We know that, but from
that's just from
the way you developed it. From the way with this Holder continuous space of Holder continuous functions, can you see how to introduce the complex structure on that space?
Okay, so we know that in general, this space of like a continuous function here, you may not have a complex structure, right? So this one is if you consider like a space of a continuous function on the sigma A, usually we define the continuous space of continuous function on the interval. We may not have a complex structure, right? But for this function, so the SG is actually subspace of this one. But this one we can have a complex structure.
So we know that there is a complex structure, but
yes, from Teichmüller's theory.
How to describe it explicitly, maybe?
So that means for this space, even that is a real function space, but they still have a complex structure.
Can you describe the complex structure directly?
Yeah, just from Teichmüller space. Yeah, that's another way you can apply Teichmüller space into the function space.
Other
Is
questions?
there a notion of tangent vectors? Do you understand tangent vectors to Teichmüller space here?
You mean tangent space of what?
To the Teichmüller space. Like you embed the Teichmüller space into the space of scaling functions.
Yeah.
And then what would be, is there a notion of tangent vectors? Like
tangent vectors, you take a smooth curve on the curve, right? You take a derivative.
Do you know what are the tangent vectors in the image?
Not yet, yeah.
So that would be maybe a way to.
Of this, you mean the T S0 SG? You mean that one, right?
Yeah.
Yeah, that one. That's still. I don't know. This one's supposed to be also function space, function vectors, but I have no idea how to characterize this.
Yeah, so maybe that would be a way to introduce at least almost complex structure using these tangent vectors and
right.
Gilbert transform.
Yeah, that's something worth to be studied. Yeah.
Very good.
Okay.
More questions? I guess just a very small comment in the very last problem that you showed.
Which one? Last?
Yeah, just before that.
This one?
The problem is to characterize the function S tau, right?
Yeah, that means which function can be scaling function.
Nothing to do with characters.
So for example, if you give a S in the C sigma A, right, plus what condition to get this one as a scaling function in SG? What conditions?
Thank you.
Oh, actually, you want to if I not if. Yeah. Oh, another word is like Teichmüller said, how do you see this tangent space like this?
Thank you very much, Professor Jiang.
Thank you. Bye-bye. So